Any other questions? Okay, so just to do a quick recap, in the last class, we saw notions of what is a linear code, the generator matrix, and the parity check matrix of a linear code. We saw that the minimum Hamming distance for a linear code is equal to the minimum Hamming weight of the code. So instead of looking at the minimum Hamming distance, we can just compute the minimum Hamming weight, right? And okay, so we saw that the minimum Hamming distance is equal to the minimum Hamming weight. We then looked at the parity check matrix and defined the dual code. So any linear code is basically the row space of the generator matrix, or it can be viewed as the right null space of an appropriate parity check matrix. And the dual code is basically the row space of the parity check matrix. And we saw a bunch of examples. So now recall that the problem of finding the minimum distance of a code was somewhat simplified for linear codes, because all you need to do is find the minimum Hamming weight. So instead of looking at pairs of code words, it is sufficient just to look at all possible code words, find the one with the minimum Hamming weight, and that gives you the minimum Hamming distance of the code. So can we do this? Can this be simplified even further? Because even this takes exponential time, right? You have to list all possible code words, and there are exponentially many of them. So can we do this more efficiently? Does the generator matrix or the parity check matrix already, is there a way of directly getting the minimum distance from one of these matrices? And it turns out that there is, and the way to do it is by looking at the parity check matrix. This somewhat simplifies the computation of the minimum distance. And so I make this claim. Okay, so given any code, given any linear code, let us say that I have nkd linear code, let h be any parity check matrix. So h is any parity check matrix for C. My claim so for this I look at another parameter, the maximum number such that every L columns H are linearly independent. So another way of saying this is the following. So if C is an NKD linear code, then every D minus 1 columns of H are linearly independent, and there is some set of D columns which are linearly dependent. D minus 1 columns of H are linearly independent some set of D columns of H linearly dependent. Is the statement clear? Okay, so why do you think this is the case? So what is H times X for any code word X? Zero. So what does this tell you? So what exactly is H times X? No, H times X for a given vector X. What exactly is H times X? It is some linear combination of the columns of H. Do you agree? So basically, whenever I take a H X H have these columns of H times X X1 times N. This is basically X1 times the first column plus X2 times the second column plus X3 times the third column and so on. So now with this particular view of the code, what can you say? Is it possible to prove this particular statement? Let's take the second part of this statement. Some set of D columns of H are linearly dependent. So what does that mean? How do you define linear dependence? Linear dependence means that if some vectors are linearly dependent, then it means that there is some linear combination of these vectors, some non-zero linear combination of these vectors, which gives you the zero vector, which is equal to the zero vector. Correct? So what does this in particular say? I can find D columns such that, and some linear combination of these D columns which give you the zero vector, right? So again, looking at this particular view, what does it say? It means that there is some assignment of x1, x2 up to xn, and you're taking a linear combination of only D columns, and the n minus, and you're not picking any of the other n minus D columns, right? So can you interpret this as whatever h times x equal to 0? What constraints does it impose on x? So in particular, if I asked you to take a linear combination of the first D columns of H, can you write it as H times X for some particular X? This is my H, right? I want to take a linear combination of the first 3 columns. Okay, how can I write a linear combination of the first 3 columns in term as H times X? What would X have to be, or what structure would X have to have? Suppose I want A times the first column plus B times the second column plus C times the third column. First 3 elements, A, B, C, and the rest would have to be 0, right? So if I had to take a general linear combination of the first 3 columns of H, then it is basically the same as taking H times X for some X where the first 3 entries are non-zero and the remaining entries are all 0, correct? So if I'm taking a linear combination of some D columns of H, then basically it is the same as taking H times X, where the number of non-zero elements in X is D, correct? Right? Or basically the Hamming weight of X is equal to D. Right? Now what does it mean for some set of D columns of H to be linearly dependent? It means that there is some D columns which are linearly dependent, or in other words, I can find some vector X, right, where only D entries are non-zero, the remaining entries are 0, and H times X is equal to 0, correct? So what does H times X equal to 0 imply? It's a valid code word, right? So the second statement implies that you can find some X with Hamming weight of X equal to D and H times X equal to the 0 vector, right? But H times X equal to the 0 vector implies that X is a code word, correct? So that basically means that there is some code word X in C with Hamming weight equal to D. Is that true? It is, because D is the minimum Hamming distance of C, or in other words, the minimum Hamming weight of C. Right? Alright, so now using the same approach, let's try to prove the first statement. We want to show that if I take any linear combination of a non-trivial, non-zero linear combination of any fewer than D columns of H, then I should always get a non-zero vector, because that is what it means for it to be linearly independent. So every D minus 1 columns are linearly independent. Linearly independent. Another way of saying this is that H times X is not equal to 0 as long as the number of non-zero entries X is less than or equal to D minus 1, but of course greater than 0. There has to be at least one non-zero entry, right? Because H times the 0 vector will always give you the 0 vector. So if you multiply by any non-zero vector and the number of non-zero entries in X is less than or equal to D minus 1, then the resultant is non-zero. Correct? And why is that true? Correct. So X cannot be a code word. Why? Exactly. Yes. So the Hamming weight of X is less than D, so it cannot be a code word. Right? So if H times X equals to 0, then weight of X would have to be at least, so therefore H X is non-zero all X with Hamming weight less than or equal to D minus 1, but strictly greater than 0. So now if I give you a particular code and I specify a parity check matrix, then all you have to do is find out how many columns are linearly independent. If you're able to do that, then you basically computed the minimum distance of the code. But now, what exactly does this involve? How many, in the worst case, how many trials are required? Suppose you wanted to do it in a brute force fashion. Correct. So let's take the matrix H. Correct. So H, what is the size of H? N minus K by N. Correct. Now what am I going to do? I'll take whatever. I'll take L columns, every set of L columns, and try to find out if they're linearly independent or not. Right. What is the complication, or what is the complexity of computing, of finding out whether some set of vectors are linearly independent or not? How do you find out if a given set of vectors are linearly independent? Yeah? How will you find the rank? Okay, it's in general not a square matrix. And what is the complexity of finding the determinant? How will you compute the determinant? You'd use the formula for the determinant, A times the determinant of this. Or that's a horrible way of finding the determinant. Okay, how do you find the rank of a? The simplest way, right? You just convert it to just do row reduction. What is the complexity of row reduction? Roughly, order in square, in cube, whatever. If I have an L by L matrix, or basically in each step I have n minus k rows and L columns, right? If I want to check if L columns are linearly independent, then I'm going to take an n minus k by L matrix and find the rank. If the rank is equal to L, then it means that it is full rank. If it is not, then stop. So what would be the complexity? What is the complexity of doing one row operation? How many multiplications, how many additions? Sorry? So L multiplication, what? Order L. Right? The number of arithmetic operations to do one row operation is order L. Right? And how many column operations are required? So this is for one row operation, right? How many row operations are required? N minus k, right? And I don't need to bring it to row reduced echelon form. As long as I just bring it to echelon form, find out whether it's a triangular matrix or not, I'm done. Right? So because I just want to compute the rank. So the complexity is order n minus k L. This is the number of arithmetic operations that are required to check whether an n minus k by L matrix is full rank. So if I want to check if L columns are full rank or not, I only have to perform these many arithmetic operations. Correct? So now I want to check if any set of L columns are linearly independent or not. How many such sets are there? N choose L. N choose L. So N choose L times order k L, and I need to do this for a number of different L's, right? I don't need to do it for one, because as long as there is one non-zero element, the rank is at least one. So I look for two columns, find out if they're linearly independent or not, then keep proceeding. Right? How many, till what point do I have to go? Sorry? D? Why D minus 1? So I don't know what the minimum distance is. Right? I'm given an arbitrary parity check matrix H, and I want to find out what is the minimum distance by n by 2. So I start with 2, I'll go to 3, 4, 5, 6, 7, 8. Why do I need to go up to n? Why do I need to go up to n? I agree there are n columns, but then do I have to go all the way up to n? So d minus 1 are going to be linearly independent, but then I don't know whether to stop at that point, right? Exactly, we don't know. So I have to go up to d, because d is going to be the point where I'll find some set of columns which are linearly dependent. So I'll have to go from L equal to 2 up to d. Up to d minus 1, they're all going to be linearly independent. As soon as I hit d, at some point I'm going to get that the rank, it is not full rank. And then I can stop. I don't have to proceed. So the maximum complexity is going to be summation L equal to 2 to d, and choose L, order n minus k times.
So this is
To find d, yes. Now, if someone told me what d was and if I had to just verify, then I don't need to go from L equal to 2 to d. I just check d minus 1 and then d. 2 steps. So this is, but now again, if d is linear in n, then this whole thing is going to be exponential in complexity. Right, because n choose L is going to be exponential in. Right? But if d is something very, very small, then it's much easier to compute. Right? Okay, so now we've greatly simplified the complexity of finding the minimum distance of a code. This is one simple way of, I mean, simple in the sense simple to describe, but it can be fairly complex depending on what the minimum distance. So that is fine. So now given any linear code, we know how to compute the generator. Given maybe it's specified in terms of a generator matrix, you can compute some parity check matrix, or given the parity check matrix, you know how to compute the generator matrix. So the generator matrix gives you a way of encoding the code. Just multiplication with the generator matrix gives you the code word. Now, to find the error correcting or the error detecting performance, you need to know the minimum distance. And now, given the parity check matrix, you also have a means of computing the minimum distance of the code. Correct? So now, how do you actually decode? Right, so yeah. So we'll see that in a minute, but right now, as you can see, the parity check matrix gives me a way of finding the minimum distance. We start with the generator matrix. Correct. So the generator matrix is helpful because it helps in encoding. Right? I take the message vector, I multiply with the generator matrix, I get the code word. So the generator matrix is really the encoder side of things. As we'll see in just few minutes, the parity check matrix is helpful in decoding. But right now, even before that, we saw that the parity check matrix tells us something more, because directly from the parity check matrix, I can find out the minimum distance of the code. And now in some cases, you may just be able to visually inspect and find the minimum distance of the code. Right? So let's maybe try it for this. So I have this is my parity check matrix. Right? I want to find the minimum distance of this particular code. Now, just by looking at this, can you give some lower and upper bounds on D? Can you give a lower bound on D or D minus 1? So D minus 1 should be at least 2, right? Because no two columns are the same. So So definitely if I pick any two columns, then they're going to be linearly independent. Okay, so D minus 1 is at least 2. What is the maximum value of D or D minus 1? Can it be larger than 3? No, can D minus 1 be greater than 3? No, I don't even want you to compute anything. Just by looking at the size of the matrix. Why? Rows and columns, right? So the rank itself cannot be any greater than 3. So if I take any 4 columns, they will be linearly dependent. So I don't even have to go beyond 3. So I know that D minus 1 is at least 2 and D minus 1 can be at most 3. Right? So all I need to do is find out if every set of 3 columns are linearly independent or not. Is that the case? Can I find any 3 vectors which are linearly dependent? Which ones? Say I add column 1 and column 2. Do I get some other column? So this column plus this column gives me this column. So these 3 columns are linearly dependent. So obviously 3 columns are not linearly independent. So D minus 1 is equal to 2 or the minimum distance is equal to 3. So at least for this toy example, we saw that it's very easy to compute the minimum distance. I didn't have to list out all possible vectors and find the minimum Hamming weight and so on. So this greatly simplifies computation. Okay, so now let's go to decoding. Right? Suppose that I want to decode over a bit flip channel. So it's a binary channel, or in general it can be any substitution channel. Basically all the channel is allowed to do is pick some certain number of locations and change the values in those locations. The input alphabet is equal to the output alphabet. Nothing changes. Okay. So now what can I do? One way is to just maintain a table. Right? You list out all possible received vectors, and for each received vector you associate the code word that you are going to declare. Approach number 1. Okay, that's what I could call array decoding. Okay, so that is one way to do decoding. But again, this takes an enormous amount of space. The other approach is to do whatever minimum distance decoding, let us. But even if I want to do minimum distance decoding, it's still not easy, because firstly I need a list of code words. Right? So I at least have to store a list of all possible code words and then find the distance of the received vector to each of those code words and find out the one which minimizes this distance. So even implementing this is not terribly easy. I still need at least an array of all the code words and then find the distance to each. So I've simplified the encoding side of things by taking a linear code, but this directly does not help me in any way when it comes to decoding. So can we simplify it at least by some extent? And that is really where the linear code helps, or the parity check matrix of the linear code helps. code words. Correct. Yeah, I'll take exponential space. Yeah. So the goal is, I mean, there's some trade-off between space and time, right? So this takes exponential time and exponential space, right? Now, for general codes or even general linear codes, you cannot beat exponential time. There's no algorithm which will let you decode a general linear code, at least no known code, known algorithm which lets you decode a linear code in sub exponential time. I give you an arbitrary code. Okay, I want a general algorithm which works for every linear code, not specific classes of linear codes. For specific classes of linear codes, it turns out that you can find other algorithms, better ones. But so right now we want an algorithm which will work for all linear codes, a generic algorithm. All of these are generic algorithms, right? So basically, I'm trying to do something better than arbitrary codes. So if I give you an arbitrary code, then one way of decoding this arbitrary code is I list all possible code words. I maintain a table of all possible code words and do minimum distance decode. Right? For a linear code, I can do the same. Right? Now I want to do something better than this. It's okay if it is the exponential time, but I want to do better than just list all possible codes, find the distance to each possible code and code word, and then find the minimum. Question is, can this be done? It turns out that the parity check matrix can help, right? And the reason why this can help is because of a specific algebraic structure that is induced by a linear code. So let's think about the space of, I mean, this is a picture which is not accurately depicting the geometry, but let's think of this as the space of all possible vectors. So this is f to the n, correct? Now what happens? So I have f to the n. Now in this, so this is a whole set of points. So if it is a binary field, then it is 2 to the n, set of all possible binary vectors of length. Now in this, I'm choosing a linear code, right, which is some subset of f to the n. And it's not just an arbitrary subset, it forms a vector space, right, because it is a linear code. Color. So some of these are code words. Okay. Now these code words, now of course, P is a subspace of f to the, correct? Now every subspace or every vector space also forms an algebraic structure called a group. Right? So if you look at only the additive structure of a vector space, right? You forget about multiplication, you forget about scalar multiplication, you only look at the properties of addition. Basically, addition is commutative, it is associative, there exists an identity element, and for every element there is an additive inverse. So any set which satisfies these properties along with this binary operation, this forms a group. So C with whatever the vector space addition forms what is called a commutative group or an abelian group. Now, one way to think about a simple additive group to think of is the set of integers. So the set of integers forms a group, right? This is not a field, right? Because why is it not a field? Which identity? Identity is there, right? Inverse don't exist, right? So for example, 2 does not have an inverse. The inverse would be half, but half is not an integer. So Z forms an abelian group, but not a field. Now think about a subgroup of this. Okay, let us take the set of all, let's say, even integers. Right? So 0 plus 2 minus 2 plus 4 minus 4 plus 6 minus 6 and so on. Does this form a group? The set of all even integers, does it form a group? Yeah? Okay. So any set with some binary operation is a group if it satisfies the following properties. One is, of course, it is closed. So A plus B is in the group for all A comma B in the group. It is commutative. Abelian group. It is commutative. So A plus B equal to B plus A for all A comma B. It is associative. So the order in which you add 3 different elements does not matter. A plus B plus C is the same as A plus B plus C. There is an identity. There's an additive identity. And for every element, there is an additive inverse. So if you take any field and restrict yourself only to the addition operation, then that forms a group. So a field is something which has an extra operation defined on it, and it satisfies more properties. So every field is an additive group, but every group is, for a group you need to add another operation. So for example, this Z comma plus is a group, but if I add the standard multiplication operation, then it is not a field. So now I give you the set of integers and the set of even integers. So the set of integers, you rightly said, is a group, right? Because it satisfies all of these properties. What about the set of even integers? Is this a group? Is it closed under addition? Sum of even integers is again an even integer. Is it commutative? Addition? It is. Is it associative? Yes. Is there an identity element? 0. Is there an inverse? So it's a group. So the set of even integers is a subgroup of the set of all integers. So take any integer A, you look at the set AZ, basically multiples of A, set of all possible multiples of A. So this positive integer. Okay, so this is a subgroup. Now, if I take any real number a, it is still a group, okay, but it's not a subgroup of z. So, for example, I can take the set of all half times z. So that is 0 plus half minus half plus 1 minus 1 plus 1.5 minus 1.5 and so on. Now that is also a group, but it's not a subgroup of z. It contains z. But on the other hand, if it's a positive integer, so 2z is a subgroup of so in fact you can write z in terms of 2z. So z can be written as a union of two disjoint sets, 2z and a shift of 2z. So set of all integers can be decomposed into the set of all even integers and the set of all odd integers. Now set of odd integers, it doesn't form a group. Can you say why? 0 does not exist. Okay. So set of all odd integers does not form a group, but set of even integers forms a group. But the nice feature, you may not have thought about it, the nice feature of the set of even integers is this set can be obtained by adding 1 to the set of even integers. Set of odd integers can be obtained by adding 1 to the set of even integers. So this is just 2z plus 1. So this is basically the set of all 2 times x plus 1, where x is an integer. So just by taking a shift of the even integers, you get the set of odd integers. You agree? So these are what are called cosets. So given any group and a subgroup, these two sets are called cosets of that subgroup in that particular group. So 2z plus 1, 2z are cosets of 2z So if I give you any group, it's a fact that if I give you any group and I give you some other subgroup of this group, then you can write the group as a union of disjoint sets. In fact, a union of disjoint cosets. Right? So, and what is this specific structure that these cosets have? They're all translates of, yeah, they're of course disjoint. They're all mutually disjoint. So the intersection is the null set. But at the same time, they're all obtained by taking translates or shifts of the subgroup. So for example, if I take z and I take, let's say, phi z, set of all multiples of phi, right? So can you tell me what shifts of phi z are going to give me z? So phi z is one coset. What about phi z plus 1? Is it a coset? So what does phi z look like? Is 0 plus 5 minus 5 plus 10 minus 10 plus 15 minus 15. What is phi z plus 1? Correct. 1, 6, minus 6, minus 4, and then 11, minus 9, 16, minus 14, and so on. Right? What
should have only 2.
So that's what I'm trying to get at. How many cosets are there for a given? Sorry? Can you repeat? So okay, do you agree that phi z is phi z plus 1 a coset? So the intersection with phi z. So firstly, it is a shift of phi z, right? And the intersection with phi z is the null set. There's no intersection at all.
Was
Correct.
that the design.
Correct. Correct.
That like
We're trying to find cosets over here.
that we confirm one.
Yes. So 5z is always going to be a coset. It is a subgroup, right? So in this case, I have one subgroup. What about 5z plus 1? Is it a subgroup? Why? So basically 6 and 4 minus 4, right? What do you get? Sorry, 6 and minus 4? Yeah, so obviously 0 is not there, right? Okay, so this is phi z. Now what is phi z plus 1? It is 1, then 5 plus 1, 6, minus 5 plus 1, that is minus 4, minus 9, 7, 4. Okay, now what would be our next case? Phi z plus 2, which is what? 2, 5 plus 2, 7, and minus 5 plus 2. Yeah, all possible remainders of 5, right? Yes. So basically I need some more. So phi z plus 3 and phi z plus 4. So basically all possible remainders of 5 are going to give me the different cosets. Or in particular, they're not cosets, but shifts by the various remainders of 5 are going to give me the different cosets. See, phi z plus 4. So basically I can write z as a union of phi z plus 1, phi z plus 2, phi z plus 3 and phi z plus 4. Correct? So basically I'm taking shifts by certain numbers. Now instead of taking phi z plus 1, phi z plus 2, phi z plus 3, phi z plus 4, I could also have taken phi z plus 6, phi z plus 2, phi z plus 3, phi z plus 4. They would give me the same sets. Correct? But these are somewhat more convenient. Intuitively it seems convenient. So in any case, I can represent each coset by the corresponding element I'm translating by. So in this case, I'm translating by 0, 1, 2, 3 and 4. So this gives me Z. So each of these translates gives me a coset, and these elements are called coset representatives. Exactly. One of them is going to be a subgroup. The others are not going to be subgroup. Can you tell me why? Simple property. They're all disjoint, right? So exactly. So only one of them can have the zero element. The others cannot have the zero element. Only one of them can be a subgroup. Okay. Correct. But this you also need to say corresponding to which subgroup. So that is why these are cosets of phi z in Z. Okay. These are coset representatives, and a nice feature it's a side point, that these coset representatives themselves form a group, at least in this example, but under a different operation, addition operation. What is addition operation in this case? So does this form a group? 0, 1, 2, 3, 4. Exactly. You take modulo addition, modulo pi addition, then this forms a subgroup, right? So now let's take some other example, say 10z, right? What will be the cosets? So the coset representatives are going to be 0 up to 9, and this will give me a z. Now does this form a subgroup? Under some other addition? And which addition? Or 10 addition, right? So no matter what I take over here, the set of all coset representatives themselves will form a group, but under some modulo addition. Now this is true in general. You take any group, no matter what kind of a geometric structure it has, and you take any subgroup, then you look at the cosets, the coset representatives. Coset representatives form a subgroup under some modulo addition. So that modulo addition has to be defined appropriate. There's a way of formalizing all of this. We might see a little more of that through the course. So if you take a course on abstract algebra, you'll see all of this. Okay, so why am I bringing up all of these? What is the main purpose? So let's think about the geometry of codes. Basically, the algebraic structure of code. So I have f to the n. Again, this is not the actual geometric picture, but this is just to give some kind of intuition. So this is my f to the n. I'm picking a linear code, which is basically a group. Okay, this is my 0 element. Maybe these are my code. Okay, so these are my code words. This is the code. Note that there's some regular pattern to this code word, because specifically because it forms a group. Basically, if I take this vector and this vector and I keep adding 2, I'll get another code word and so on. Right? So I have this group structure. So my code is basically the set of these yellow points, and now I can look at the different cosets of this particular code. You basically take a yellow point and you shift a yellow point to the right. Okay, that gives me the set of all green points. Right? That's the geometry that is going on here. Now, if I shift all the green or all the yellow points up by 1, then I get these blue points. Correct? So these are this forms the set of blue points forms another coset. Yeah. Fn is the set of all points. Each color represents one particular coset. So I take the yellow point. So this is my code. So every yellow point is a code word. I shift it up. I shift it up 1 unit. I get the coset of blue points. I shift it right by 1 unit. I get the set of all green points. I shift it up one step and right 1 step. I get the set of all orange points. Okay. So these are all the possible cosets. Correct. 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 So I can call this whatever 0 0, 0 1, 1 0, and 1 1. Correct. These are the 4 coset representatives. Correct. Now these points under modulo 2 addition, you can verify that they form a group. So component wise modulo 2 addition. Can you see that? So 0 0 0 1 1 0 1 1 under mod 2 addition, just F2, right? Or Z2, sorry, F2 square or Z2 square. So this is basically the group that so this was my Fn, and this is my C, my code, and these are all the various coset representatives. So the code words are only the yellow points, right? So one of these yellow points would have been transmitted, but I could have received any of these other points. The goal is to understand how do I do, say, minimum distance decoding using something, right? So now if you had to characterize a minimum set of error vectors, right, how would you do it? Take any, so now there is this regular pattern, right? Since it's a linear code, it forms a group, and since it is a group, the code words are kind of regular. If I sit at this particular location and I look around at all the possible code words, I get one particular view. But if I sit over here and look at all the code words, I get the same view, right? Because if I take C and add any other code word, I get back C, the same set. Correct? For example, if I take 5Z and add 10, what is the set that I get? It is still 5Z. Nothing has changed. So that is what I mean when I say the view around any code word is basically the same. Yes.
So
okay.
we consider big one.
Yep. These under mod 2 addition.
Coset representatives, 0, 1.
These are the coset representatives. Right?
So we can consider coset 0, 1, 2.
0 0 0 1 1 0.
Earlier.
Earlier. These are
So
correct.
So diagram, if you
It is not the same structure. The two groups are not the same. Why? Because let us say I have one. Right? In this case, let's take 4Z. So they have the same size. You're asking whether this group structure is the same as whatever 4Z, right? You take 4Z and look at the cosets of 4Z, correct? So the cosets would be 0, 1, 2, 3, correct? In this case, I have 0, 0, 0, 1, 1, 0, 1, 1, correct? You're asking if this group structure is the same as this group structure. The answer is no. Reason being, let me take 1 here, okay? I add 1 to itself. What happens? I get 2. I add 1 once again. What do I get? I get 3. I add 1 once again. What do I get? Right? So this in some sense is like cyclic. Correct? So I add 1. I keep adding 1 to itself multiple times. I run through the entire group. Correct? Now take this particular case. 0, 0, 0, 1, 1, 0, 1, 1. Take any element of this. Let's take 0, 1. Add 0, 1 to itself. What do you get? 0, 0. Take 1, 0. Add 1 to itself. What do I get? No, 1, 0. I add 1, 0 to itself. 0, 0. Take 1, 1. Add 1, 1 to itself. 0, 0. Correct? So I take any vector in this particular or any element in this particular group, add it to itself, I always get 0. Correct? But that does not happen here, as you can see. Right? So two groups can have the same size, but they can have a completely different algebraic structure. this has a different algebraic structure than this particular group. So this, as it happens, if this is a cyclic group, you can take that there is some element such that you add that element to itself and you get the entire group. But that is not the case over here. This is not a cyclic. So it's a useful point to keep in mind, and we'll see this as we explore finite fields in a little more detail. Okay, just because the size is the same does not mean that all the algebraic properties are the same. They are both groups. They're both groups of the same size, but they're not the same group. They're not isomorphic to each other. There is no one-to-one mapping between the elements which will give you exactly the same operation. It is not. Yeah, these two are not isomorphic. Okay. So let's go back to what we are trying to do. So I have these code words, the yellow points, but the received vector can be any one of the other points. What is my goal? My goal is, given any of these points, I want to find the closest yellow point to it. Okay, that's my goal. That's my decoding problem, right? Given any point, given any point in this set, I want to find the closest yellow point. Now what I can do is, basically, in the earlier what I was doing was I maintain a set of all the yellow points, right? I save all the yellow points in memory, and given any point, I find the closest yellow point. I compute the distance, and then I declare that as my output. Okay. Now what I'm trying to do is slightly different. Now suppose okay, so one point to keep in mind is that no matter which yellow point I am at, as I mentioned, since it's a group, it looks the same from everywhere else, right? So now I get a particular received vector. Okay. Suppose I had a way to identify whether it is a green point, an orange point, a blue point, or a yellow point. Somehow magically someone tells me that. Okay. It doesn't tell me anything else. It just tells me whether my color. Okay, given the received point, it tells me the color of that particular point. You get that information somehow. Then what would you do? What would be your decoder? Suppose I get a green point. Okay. Which one would be the closest point to it? Say this point. Let's say that this is the received vector. Okay. Now obviously this and this are at equal distance, right? But let us say that I always take the one to the left. If there is a tie in distance, I take the one to the left. That's going to be my decoding rule. Okay. So if I get any green point, the closest code word is going to be the one that is just immediately left to. If it is an orange point, which is going to be the closest code word, this yellow point, I can declare that as my. Right now, in principle, these 4 points are equidistant, but I need some way of systematically identifying the code. So I will declare this as the code word, the closest code word. Okay, that is going to be my minimum distance decoder. That is how my minimum distance decoder works. Now what do I do? But note that there is this symmetry, right? So given any orange point, basically all I need to do is subtract 1, 1. Right? If I receive any green point, all I need to do is subtract 0, 1. If I receive any blue point, all I need to do is subtract 1, 0. Right? So if I have a way of identifying the color of the received vector, basically which coset it belongs to, all I need to do is subtract the coset representative and I get the nearest code word. So basically at the receiver, I need a way of finding the color of the received point. Then I only need to store this table, right? So for a blue point, I need to do this. For an orange point, I need to do this. For a green point, I need to do this. So this is great savings in memory. But whatever, I need to do some sort of computation to find out what is the color. Correct.
So we are many yellow.
That's okay. I need one decoding code. So that is okay. So I receive a vector, right? Let us say I receive this particular vector. Now what should my minimum distance decoder do? It should decode to this point, right? So one way is to find the distance to all of these points and then declare this as the minimum. Now my new decoder, what I'm going to do is, firstly, I have some magical way of finding out the color, right? I find out that it is an orange. Okay. Now what else am I going to do? I'm going to store this particular table over here. I know that it's a yellow point, so I subtract 1, 1. What do I get when I subtract 1, 1 from this vector? I get this vector, which is the one that I had to decode to. You're not discarding that information.
Yeah. Right?
You need both. You need the received vector, of course, right? But from the received vector, I'm kind of throwing away some of the information temporarily, okay, and using that to find. Essentially, if you think about it, this is kind of the error vector. I can write the received vector as the code word plus an error vector. I'm trying to find the smallest error vector. So instead of searching over code words, I'm trying to in fact search over error vectors. That's exactly what I'm doing over here. So given the code word, guess the error vector, subtract the error vector, and you'll get the code word. And if the rate is sufficiently large, right, as long as the rate is not too small, number of error vectors will be much smaller than the number of code words. Rate, that is number of code words, right? Ratio of k by n. That is the rate of the code. So here, basically, what am I going to do? I'm going to store a table of possible error vectors. Okay, not all possible error vectors. So in this case, 3 error vectors: blue, orange, and green. Now, again, if this is too large, if this is larger than the size of the code itself, then there is no point. I've got no savings at all. But if this is sufficiently small, then I'm happy. Yes. So if the rate is very, very, very small, so what am I doing over here? I'm storing a list of cosets. Correct? If the number of cosets is larger than the size of the code itself, then I'm not losing space. I'm not saving space, right? So in particular, suppose I have f to the n, correct? I have f to the n, and I have a dimension k subgroup or a dimension k code, right? What is the number of elements in f to the n? Yeah, size of f to the n, or if it is binary, then it is 2 to the n. What is the size of the code? 2 to the k. If the code has dimension k. So how many cosets will be there? Remember that the cosets are all disjoint, and the union gives me f to the n. 2 to the power of n minus k, because I should get this, the n minus k times 2. So there are 2 to the n minus k possible cosets, and I'm storing, what I'm going to do is basically store a coset representative. So if the number of coset representatives is larger than 2 to the k, then there is no point in wasting space. So this is advantageous only when number of coset representatives is reasonably small. Okay. So now, at least intuitively, we have a way. Right? So coset representatives, error vectors correspond. So the color corresponding to each color, I store a vector. I need a way of finding out what is the color, and then I just need to subtract that particular error vector to get the decoded code. So now we'll see how to get the color, right? And for that I'm going to use the parity check matrix. Right? So what is the code equal to? The code can be written as set of all vectors. So the code is basically the set of all vectors in f to the n such that h times x is equal to the 0 vector. Correct? So this, as we mentioned, forms a group. Right? Now let me look at different cosets. So I define E as the set of all x in f to the n such that hx to h times for a given E. Maybe I'll take this to B, some vector B. X C subscript B. So if B is non-zero, then obviously this is not a group. Right? But again, this is not equal to the code either. This is a translate of the code. So now each of these forms a coset. Right? As long as E is not a code word, h times E is not equal to 0. So h times x is non-zero. So that gives me one particular coset. So how many different error vectors do I need to consider? I need one coset representative for each of the cosets. And that is basically what I'm going to do. So for any x, h times x is what is called the syndrome of x. Okay? So this is the syndrome of x using the parity check matrix H. So now let me collect all possible code words or all possible vectors which give me one particular syndrome. That basically corresponds to the ones which have the same color. That forms one coset. So all vectors which have the same syndrome forms a coset. Right? So now all I need to do is store coset representation. So what is my decoding rule, or how does the decoder work? So first, like before even receiving anything, you store the following things. So for each coset, store error vector, or basically the element with the least Hamming weight. So for example, here, what was the representative we used for the green points? It was this particular vector. It is 0, 1. Right? Because in principle, I could have also chosen this to be 0, whatever 3, right? That would also give me a coset representative, but I want a coset representative which is nearest to 0. So I'm going to choose coset representative of the least Hamming weight for each. And how do I represent each coset? Each coset is basically indicated using the syndrome. So how does the decoder work? So given the received vector y, you compute h times y. So this is the syndrome of y. So given this syndrome, you know which coset it belongs to, and for this coset, you know what the error vector should be. You subtract the error vector. So corresponding to each syndrome, you have error vectors. Subtract the error vector corresponding to that syndrome, and that gives you your estimate. Again, in certain regimes, this is good because you're saving a lot of complexity. Yeah, so basically, S, the syndrome tells me which color it is. Each syndrome represents one particular color, and for each color, I'm storing one representative error vector. So once I find the color of the received vector, I'm going to subtract this representative vector and the closest code word. Any questions? Correct. So it's basically the same point, right? So if I look at, so you can view 5z, 5 times z, as though you're looking from the 0 point. Right? You look to the left, you look to the right. So that gives me one particular view, this is 5z. Now suppose I look at the same set from the point 10. which is basically 5z plus 10. Has the set changed? It has not. It is the same set. That is what I mean by the view not changing. Any other question? Okay, so let's stop here.